In this video here, we're going to take a look at static particles. So what do we mean then if a particle is static? Well, a particle, or this could also include a rigid body, is in static equilibrium if it is at rest and the resultant force acting on the particle is zero. So before we take a look at any problems here involving static particles, let's just consider a methodical approach to solving problems in statics. So the very first thing that we're going to do here then is start by drawing a force diagram showing clearly where the forces are acting on the particle. We will then resolve the forces into horizontal and vertical components, and if the particle is on an inclined plane, the components will then be parallel and perpendicular to the plane. We then set the sum of the components in each direction equal to 0. And then finally here, we're going to solve the resulting equations to find the unknown forces. So a very quick introduction here to static particles, but in terms of an introduction here, we don't need too much more. Okay, so we will develop this in more detail as we work through this chapter, but for now, that gives us everything that we need here. So let's just take a look then at one quick practice question. So let's just take a look then at this one practice question here for static particles. So straight away, what we can see here for this question is we have this diagram. And this diagram here shows a particle in equilibrium under the forces shown. So there is a number of different forces here acting upon the particle. So the question then says by resolving horizontally and vertically, find the magnitudes of the forces P and the force Q here. Now, before we can resolve horizontally and vertically here, what we need to do is take these two forces then of 6 newtons and P newtons here and split those two forces into horizontal and vertical components. So to do that here then, let's just use a different color. So for the horizontal components then, let's do this in red here. And now for the vertical components then, let's do this in blue. Okay, so altogether, we'll get something that looks, say, like this here. Okay. What this forms then is a right angle triangle. So in that case then, we can use basic trigonometry here. So for the horizontal component then of the 6 Newton force, what I get here is 6 cos of 60 degrees, like so. And now for the vertical component here, what I get then is 6 sine of 60 degrees. Okay. So nice and straightforward. All we've done here then is split the 6 Newton force into a horizontal component and a vertical component. So we're now going to repeat this here then for the force of P newtons here. So again, let's use our pen colors here to show the horizontal and vertical components. Again, just using red for the horizontal component. And again, we'll use blue here to show the vertical component. Okay. And again, this just forms a right angle triangle here, like so. So now for the horizontal component here then, what I get is P cos of 45 degrees. And now for the vertical component here, I'll just do it above just so I have enough room then. What I get here is P sine of 45 degrees. Okay. So we now have a good starting point here, right? We split these two forces into horizontal and vertical components. So we've now got everything that we need then to resolve horizontally and vertically to find the magnitudes of the forces P and Q here. So we just start then by resolving horizontally here, right? If we resolve horizontally here, taking to the right as positive then. So taking to the right as positive here, what we need to consider is what forces are acting horizontally to the right, which in this case is simply this one force of 6 cos of 60 degrees. And because that's acting to the right here, that would be positive, right? Because we've took to the right as positive. So we get 6 cos of 60 degrees, like so. We now consider what forces are acting horizontally to the left here, which in this case is just this single force of P cos of 45 degrees. We get minus P cos of 45 degrees there. Okay. There's no more forces acting to the right or to the left here. So in that case, then this will be equal to 0 here because the particle is in equilibrium. Okay. Now we're looking to find the magnitude of the forces P and Q here. So we've got this equation here. What we want to do is solve for P. So I'm going to add P cos of 45 degrees to both sides. In that case, then I get P cos of 45 degrees is equal to 6 cos of 60 degrees. Okay, like so. Well, cos of 45 degrees here, that is 1 over root 2. So I've got P times by 1 over root 2. So I get P over root 2. I get P over root 2 here. And that is equal to 6 cos of 60 degrees. Well, cos of 60 degrees is a half. So 6 times by a half here is 3. So in that case, then, for P, it would simply be 3 root 2 here. Just times in both sides by root 2, right? I get P is equal to 3 root 2 there. Okay, so that gives us the magnitude of the force P, but we also need the magnitude of the force Q here. So to find the magnitude of the force Q, what we're now going to do is resolve vertically upwards, okay? If we resolve vertically upwards here, or taking upwards as positive, I should say, like so. So let's start then by considering what forces are acting upwards here. Okay, well, obviously we've got Q here. If I get Q, I've also got this vertical component here, right, of 6 sine of 60 degrees. That's acting vertically upwards. That would also be positive here. I get Q plus 6 sine of 60 degrees, like so. And again, I've also got this vertical component here of P sine of 45 degrees. So plus P sine of 45 degrees here. Okay. We have no more forces now acting vertically upwards. We now need to consider what forces are acting vertically downwards, which in this case is just a single force of 10 newtons. So because we took upwards as positive here, this force of 10 newton that is acting vertically downwards, that would be negative here. Okay, so that's going to be minus 10 here. And this is equal to 0 because the particle is in equilibrium. So because we're now looking to solve for Q here, what I'm going to do then is take everything else to the other side. In that case then, Q is equal to, so I get 10 minus 6 sine of 60 degrees minus P sine of 45 degrees here. So 10 minus 6 sine 60 degrees and minus P sine of 45 degrees here. Okay, well, sine of 60 degrees here, that is root 3 over 2. So 6 lots of root 3 over 2. That would just be 3 root 3. Okay. I get 10 minus 3 root 3. Therefore, Q is equal to 10 minus 3 root 3. And then for P sine of 45 degrees, well, P is 3 root 2. We've already established that. So what I've got then is 3 root 2 times by sine of 45 degrees, which is 1 over root 2. So I've got 3 root 2 times by 1 over root 2, like so. The root 2's will just cancel here, like so. So what I get then is minus 3 here, which if we simplify them, just gives us Q is equal to, so 10 minus 3 is 7. I get 7 minus 3 root 3 here. Okay. And there we have it. So as you can see here, right, we've got the magnitude of the force P, and we also have the magnitude of the force Q. So it's up to you. You can keep it in exact form like this here. Or you could just put this into your calculator and round that to say 3 significant figures. Same applies here to P. Either's fine. I'll just keep it in exact form, just so it looks a little bit neater. Okay. But there we have it. So that gives us the solution to this one practice question here. And that brings us to the end then of this video here on static particles.